next interesting presentation is by Christian Skafte Bæk Clausen from the University of Southern Denmark. He will be presenting his paper on a modifiable architectural design for commercial greenhouses, energy economic dispatch testbed.
All right, thank you all for being here. And I would like to present this paper. As Christopher just mentioned, the title is a modifiable architectural design for commercial greenhouses, energy economic dispatch testbed. So it's a long title, but let's try to break it down. So first, I would like to get a motivation and background behind this study. Then I will give the methodology, and then I will present the software architecture, and then I will go through the scenario in the study, and then I will give the results and discussion, and finally give the conclusion and future work. So first, to establish some background and motivation. So of course we have a global rise in energy prices and incentives to reduce CO2 emissions. And also when we talk about commercial greenhouses, they have a goal to minimize the energy costs and also the CO2 emissions. So these are the two goals. And at the same time, the greenhouses want to fulfill the energy demands, so such as temperature and heat. And there are some problems in doing this or providing a solution for these goals. So first of all, in this study, we want to minimize, of course, again the cost and emissions, and we do that by controlling the various energy systems within the commercial greenhouse. And the first problem is that we have multi-model energy production units. So we have a combined heat and power plant. We also have heat pumps and thermal energy storage. So that's one problem. We also have dynamic energy prices and CO2 emission signals. So when we buy electricity, the market is dynamic. And also the CO2 emission signals depends on, for example, if there has been produced renewable energy in a given hour. Then there are also problems with changing business requirements due to operating constraints and policies. Then there's the problem of strategic decision-making in a multi-objective landscape. And finally, there's a problem of experimentation and verification within a physical domain, because that exposes the business to significant risks. Okay, so the background, this paper extends the previous work where we tried to minimize the costs in a commercial greenhouse. So we have the field of economic dispatch where we try to allocate resources efficiently. And then we have multi-objective optimization where we try to optimize multiple objectives. And finally, we have the area of modular or testable software. And there's plenty of literature regarding economic dispatch and also multi-objective optimization, and of course modular or testable software. But there's a gap on how to make modular, testable, and testable software in these two areas. Okay, so the methodology used is something that is called attribute-driven design. So the purpose here is to establish an initial architecture that is modular, and it should also address the key architectural issues, so changing business requirements and experimentation. And we want also to have enabled iterative refinement, so we can refine the architecture. And then finally, we want to delay design decisions that do not affect the overall architecture. And so we first start by identifying the stakeholders, then we derive the high-level requirements or business goals, and then we find the architectural significant requirements, and then we can use those to make a core architecture. Great. So this is the initial core architecture. So you can see here the dotted line boundary here around the core architecture. So it comprises of several elements. So we have an optimizer. This is what I will talk about today. Then we have an energy systems emulator. So that's an emulator or model of the greenhouse energy systems. And then we have a graphical interface. And finally, we have some external inputs because we need energy prices and also energy demands and CO2 emissions to be fed into the optimizer in order for us to do an optimization. Okay, so I will dive into the optimizer because, as I said, this was an initial architecture. And then we dive into the specific of the optimizer, because this is a significant concern. If we cannot optimize then we have no valid reason for conducting the rest of the architecture. Okay, so the modular architecture separates concerns behind well-defined interfaces, and this also means that every module can be configured or reconfigured to satisfy changing business objectives. So what you see in the figure here is that you have several modules. The above bar here, optimization application, sort of encapsulates all these modules. And so we see that we have an external inputs module that is responsible for mapping the external inputs into something that the application understands. Then we have a multi-objective algorithm where we can define decision variables, objectives, and we also have some virtual models. And we also have a decision maker module that is responsible for the decision strategy. And finally, we can output or give the output of this optimization to the energy systems emulator. So the flow here is that we have external inputs that goes into the optimization or the optimizer module. Then it initializes the optimization, and then we conduct the optimization by evaluating on virtual models. And then we, when the optimization has terminated, we can select a single strategy to operate our energy systems. And finally, we can emit a schedule that can be used to control the energy systems in emulator. So the scenario here is that we have some virtual models. So in this case, these models were derived from data in a real greenhouse. And in this case, we have a CHP, a gas boiler, a heat pump, we have a district heating model, and also we have a thermal energy storage model. These are gray box models. They were developed in Modelica and then exported to functional mockup units that provides a functional mockup interface that we can integrate into the optimization. So each of these represents a physical counterpart in a real greenhouse. They can be controlled through their control variables. So we can use that to optimize how we can control these models. So for the definition of the multi-objective problem, we optimize over a horizon of 1 week, and the objectives follow that we want to minimize the cost of the whole plan or schedule. So minimize gas cost, electricity cost, and district heating cost, and then we have some income because we can produce electricity within the greenhouse. Then we want to minimize the CO2, and we can do that by calculating the emissions, so the emission of gas, electricity, and district heating. And then we have some constraints where we just say that we cannot use more power than what is available on the grid. And finally, we cannot use more energy than what is stored within the thermal energy storage. And of course, we also have some resolution limits on the control variables to limit the solution space. So the table here on the right just shows how a energy dispatching schedule looks like. Okay, so the external inputs, these are forecasts. So we need forecast for the length of the horizon in order to do an optimization. And since we need to evaluate the economics of a schedule, we need to have energy price forecast and CO2 emissions forecast. Fortunately, we have this for the electricity signals, but we don't have it for gas, and we don't have it for district heating. So we just use constant prices here, and then we The same is the case for the emissions, the CO2 emissions. Then for the energy demands, these demands were taken from a real greenhouse. So what you can see here is that we have a fluctuating heat demand and electricity demand over this period of 1 week. So for the results, what you can see here is that we have a Pareto frontier. So the gray dots represents invalid solutions that do not satisfy our constraints. And the red dots shows the valid solutions that satisfies our constraints. And then we can see that we need to make a strategic decision because these objectives are in conflict. So we can either choose to minimize the CO2, choose a compromise, or minimize the cost. And what we can see is that cost can be reduced by 1.11% at the cost of an increased CO2 emission of 12.74%. So for the discussion here, the CO2 objective was integrated without affecting the existing implementation. So remember, this study works or extends previous work. And also, more precise CO2 emissions input signals are needed for gas and district heating to reflect reality, of course. And then when we use FMUs, this is native C code, there's a significant overhead in this case because the optimizer runs in Java. So we have an overhead of calling C code. And then we also need to validate the approach in a real-world application over an extended period of time, of course. And also we have a tight coupling between decision vectors. This is the control variables, and then the objectives, and also the FMUs. These are tightly coupled, so this increases the modification costs. So all in all, we can say that the modular architecture for, or we provide a modular architecture for experimenting and verifying economic dispatch algorithms. And we also demonstrated that the architecture demonstrated modifiability to accommodate the requested change of incorporating CO2 emissions into the decision-making process. So for future work, we want to implement the remaining subsystems, and we want to also assess modifiability in the decision vector and lower the coupling to the objectives. And we also want to assess the costs associated with modifying the optimization problem to account for adding or removing energy production units in the greenhouse. And then we also want to identify other relevant objectives, such as favoring energy production units within the greenhouse due to impairment or maintenance reasons. And then, of course, finally, we want to verify the architecture in a real-world case study. Yeah. Thank you all.
So thank you for a nice presentation. And now we have time for some questions. Yes.
Thank you for the presentation. Like you mentioned that you are predicting over a week, for a week horizon, right?
Yeah.
So, like, I have a question. Like, what are the parameters you are considering for predicting, and what kind of prediction algorithm do you use? You use regression or probabilistic prediction? And the other part of the question is like, what are the dynamics which you are considering? Because 7 weeks time is a long period, right? So there will be dynamics which gets changed, and due to which the environment, there will be changes in environment. So what are the dynamics which you are considering for this, and how, like, and what will be the impact, so for 7 week horizon, because like if you're taking for a 1 week horizon for 7 days, if you're taking a long term prediction, there might be some, like, like when you average it out, there might be some flexibility of control, right? But however, when you have a smaller prediction horizon, let's say 2 minutes or 5 minutes, the accuracy should be higher. So like, how do you think like your model will be performing if you have a smaller horizon?
Okay, so the consideration here is that we want to use model predictive control. So as I showed the initial architecture, we have the optimization, and we can reduce the horizon over which we optimize. So we can, for example, go down to 1 hour and then refine the optimization, run the optimization multiple times, and then the results should be better than optimizing over 1 week, right?
Yeah. So like for the model predictive control, you need to have some of the dynamics to be included, right? So what are the dynamics you are considering?
So
You cannot have a model prediction algorithm without some dynamics, right? It should include some dynamics for that.
so here the dynamics are, of course, the input price signals, right? And then we also have the models. But I'm not sure exactly what you mean with the dynamics here.
We can discuss later.
Yeah, sure. Yeah.
Thank you. Do we have time for one more question? Do we have any? Yeah.
Yes, thank you for the nice presentation. Could you explain a little how you select the compromise solution from the Pareto front?
Yeah, so we have a module for that. It builds on previous work. So we have different metrics on how to select from the Pareto frontier. So we can, for example, average all the objectives out. So in here we have price and CO2, right? And then we can normalize these objectives because they might operate on different scales. And then we can normalize it and use the normalization to compare the different objectives, and then perhaps take the average, or we can just select the minimum and maximum. So this entirely depends on the decision maker that operates the system. Of course, here you can have a real human being operating, right? You could also have an autonomous system. We are not at this stage yet because it also requires the operator to, trust in this kind of system to run autonomously. But we have several metrics on deciding the strategy from the Pareto front.
Thank you.
Yep.
Yes, and that concludes this presentation. So if anyone should still have a question, you can feel free to reach out to Christian in the breaks.